And where we're at is we're essentially taking a look at the rotational version of Newton's second law. Okay. And so, as we know, our Newton's second law, the special case we usually work with is F equals ma. And then if we go in and convert this into rotational topics, then what we get are the net torque, and then the mass becomes the moment of inertia, and then our acceleration becomes the angular acceleration. So the net torque is I alpha, is kind of our new version of Newton's second law. Okay. And the things that we picked up was we picked up that the torque, that torque was R cross F, and we learned how to evaluate the cross product. We could also have a nice formula to get the magnitude, and then we could do our right hand rule to get the direction. So that's a definite option. And then in general, our moment of inertia is the integral of like r squared dm. And we showed how to do that for the rod. And I did two different ways, the center and then the end. And then, oh yeah, we should write down the parallel axis theorem. So the moment of inertia about a new axis parallel to an axis through the center of mass with its moment of inertia. What you do is you add the entire mass of the object times d squared, where d is that shortest distance between the two parallel axes. And you can shift from one moment to another moment. And like I said, this is kind of a new thing, is that, it was the same rod, but we rotated it through a different axis, and then the moment of inertia changed. There is no translational counterpart to that. Okay. It's not like an object has one mass if you move it horizontally and a different mass if you move it vertically. It doesn't behave like that. But if you change the axis of rotation, then you change the value for the moment of inertia. So all of these rotational quantities are defined relative to the axis of rotation. Okay. And so there we go. So